Neurons store their energy in the form of charged particles. We're going to talk about the position and movement of these particles over the next few minutes. So just bear with me. I'm going to introduce our main characters here. Sodium, or Na+, and potassium, written K+, ions are both positively charged, like the positive or negative end of a battery, or the positive or negative end of a magnet. The inside of the cell at rest, when the neuron's not sending a message, not doing anything, is negatively charged. And this is because even though there's positively charged K+ particles in there, we have large negatively charged proteins in there that don't go anywhere or do anything. So that's why we don't talk about them much, and they're not on the diagrams. So just know that the inside of the cell is negative at rest. The outside of the cell is positively charged compared to the inside. So the voltage difference across the membrane is what we're most interested in and what causes this buildup of potential energy, which is why we call it resting potential. Positively charged potassium ions are more concentrated inside the cell than outside. Even though they're positive, remember the inside of the cell is still negative from those large proteins that outweigh these little positive particles. So just keep in mind it's negative here. The sodium ions are more concentrated outside the membrane, and there are channels or gates that could allow each type of particle through. There are sodium channels. There are potassium channels. There's a sodium-potassium pump. We'll talk about its function later. Don't worry about it just yet. These channels or gates are closed at resting potential, especially these sodium channels. Now, the potassium channels are open, but potassium's not really going anywhere. We're going to talk about why, even though the gates are open. Sodium channels are firmly closed at resting potential. Now, some of these particles kind of want to move. Their nature would be to drift around. There are two forces of nature operating on these two types of particles that try to influence them to move, but they actually can't because the channels are closed. First, our first law of nature here is called opposites attract. It's a force of nature that operates on electrical gradients, meaning if there's a difference in charge, positive versus negative, opposites are going to want to attract. Negative and positive particles want to come closer to each other and kind of cancel out the charge and make it neutral and zero. The sodium would want to go towards the negative inside of the cell, but they can't because the channels are closed. Potassium's electrical gradient would want it to go where? It is a positive particle already inside a negative environment. So it actually wants to stay put. It's positive and it wants to be in near that negativity. So it's attracted to stay inside the cell. But remember I said there are two forces of nature operating on these two different particles. We have another force of nature at work. We also have what's called a concentration gradient, or our law of nature here is diffusion. Diffusion means that when you have a lot of the same substance concentrated close together, it's generally going to want to spread out. And it's going to do that unless there's barriers in the way. It's going to spread out until it's evenly concentrated everywhere. Just like a gas in a room or a liquid in a container, it's going to spread out to fill the whole thing. A liquid in a container is not going to stay in one little spot, right? It's going to fill the container shape. So let's think about what the concentration gradient would influence each of these two particles to do. You can pause the video and take the quiz that kind of sums up all of these, or you can stay with us here. So the concentration gradient would make the sodium, where there's a bunch of it outside, to move inside where there's not much sodium. So it has two forces of nature pushing it in the same direction. Electrical and chemical gradient are telling it to go inside the cell. Potassium, on the other hand, it's a little more complicated. If we're not thinking about the electrical charge at all, nothing about positive, negative, just the concentration gradient, there's a bunch of potassium inside and very little outside. So that would influence the potassium to want to leave. So just to sum this up really quickly, sodium has two forces of nature telling it to do the same thing. The electrical gradient says, positive particle, go into the negative inside of the cell. The concentration gradient says, sodium, there's a bunch of you here, spread out, go to the inside where there's not a lot. Potassium, on the other hand, is subject to competing forces of nature. Its electrical gradient, or opposites attract, say, you're a positive particle, stay here in this negative space. However, the concentration gradient says, potassium, you're really crowded in here. There's not a lot of y'all outside. Why don't you spread out and go outside? Because of this, these two forces of nature almost cancel out. So the potassium is just going to stay put. Now, the concentration gradient is slightly more powerful. So remember I said the potassium channels are open. A little bit of potassium escapes. But this is where we come in with the sodium-potassium pump. Sodium-potassium pump brings back in some of those escape-y potassium ions so that we still keep the same concentration and the same electrical charge that we started with. And if for some reason the sodium channels were opened and sodium got in, the sodium-potassium pump would pump the sodium out, and it keeps bringing back in those extra little escaping potassiums. So we are at resting potential, and we are keeping these particles where they are until the cell receives an electrical message. But to kind of drive home the way these particles and their forces of nature work on them, I like to think of this admittedly very heteronormative example, but I like to think of kind of a club or bar example. Think about the club does not like to be filled with a whole lot of heterosexual dudes. They want a lot of ladies in their bar that's going to attract a lot of straight dudes, right? So they tend to give like ladies' night discounts. So let's imagine that these potassium particles, potassium ions inside the cell are our ladies. They're hanging out, and a few of them might be leaving, but for the most part, a couple more will come back in. We keep this club just filled with women. And because opposites attract, that's going to make our straight dudes waiting outside, ready to get into the club, really excited to get into the club. They want to be in there. And there's not a lot of dudes in there, so that's your concentration gradient too. But the bouncer is keeping the door closed and not letting any of these dudes get in. But they are lined up and just ready to go as soon as the doors open and they were to let in any men, they're going to go in there.